this kind invitation in this nice conference in this wonderful city. It's a pleasure to be here again. My name is Carlile Lavor. I'm from Brazil. And in fact, this is I joined work with Liberti from École Polytechnique here in Paris. And now he's getting a sabbatical here in New York in the Research Center. And Jorge, Alencar and Germano are PhD students in Brazil. So I will talk about distance geometry problem. And essentially, distance geometry is the study of geometry based on the concept of distance. Yeah? So first, I will explain the definition of the main important problem in distance geometry, and it's called distance geometry problem. So the basic idea is to calculate immersion of graphs in some Euclidean space. Of course, we can generalize to other space, but we are interested in the immersion of graphs in some Euclidean space. So the formal definition is the following. So given an integer k, an undirected simple graph where we have non-negative numbers associated to the edge of the graph, the problem is to ask if there is a function where we can realize the set of vertices in some Euclidean space. And the dimension of the Euclidean space is given a priori by the parameter k. So the problem is it possible to realize these vertices in such that when we associate vertices of the graph with some points in some Euclidean space, we can calculate the Euclidean distance. And if the question is that if these Euclidean distances are equal to the distance to the edge, to the values associated to the edge. So some facts about the distance geometry problem. For k equal to 1 is NP complete, and for k greater than 1 is strongly NP hard. We were motivated by problems related to protein structure. So we will consider here, we will fix a k equal to 3, but the majority of the results can be extended to higher dimensions. So this is the problem that we are interested in. So in the literature, the main methods in order to try to find this embedding are continuous method. And this problem can be modeled by a global optimization problem. And one of the most used functions is like this. So we want to minimize this function. And of course, we know that the global minimum is 0, and we want to try to define the realization of vertices u and v when we have an edge associated to this edge. So the main problem of this optimization problem is that in one dimension we have a situation like this. Yeah, we have a lot of local minimizers and also maybe global minimizer, and we want to find at least one global minimizer. And one of the problems is that the quantity of local minimizers increases exponentially with the number of the vertices. So, but we can explore the structure of the graph in order to use other methods. For example, if the graph if is rigid, we can prove that the search space is a discrete space. So, and there are in application there are many situations where the graph is rigid. We are interested in this case. For example, in the problem related to the protein structure, we can prove that we have some conditions in order to make the graph rigid. So we can consider some hypotheses where we can prove that the search space is finite. Where is the main condition on this? The main condition, the main hypothesis is that that there is an order on the vertices of the graph satisfying these two hypotheses. So first of all, we consider this is a distance geometry problem where we have an order or an ordering on the vertices satisfying these two hypotheses. So in this case, it means that the search space can be finite, and this is why we put the name discretizable. And since we are interested in protein structure, we fix the dimension. We are interested in the space, and this is why we put the name molecular. So this is a class of subinstances of the distance geometry problem, and we call it DMDGP. So if there is an instance of distance geometry problem and an order satisfying these two hypotheses, we can prove that the search space is finite. So the first hypothesis means that for each 4 consecutive vertices in this order, we have a clique. So it means that for 4 consecutive orders, or think about atoms, it means that we have known distance related to these atoms. And this is the main hypothesis. The second hypothesis is a technical hypothesis. It means that in addition to satisfy the triangle inequality, we require that we satisfy the strict triangle inequality. Why? Because if we have 3 points perfect aligned, we cannot discretize the search space. And we have the same question. So the intuition behind this discretization is the following. Suppose that we have 4 consecutive vertices, and if we have all of the distance related to these 4 atoms, and we fix the first 3 vertices, it means that there are just 2 possibilities for these vertices. Why we define this hypothesis in order to discretize the distance, the search space of the distance geometry problem? Because suppose that we have atoms, and this is a backbone of a protein, for example. So we can this edge we know a priori because it's related to a covalent bond. We also know a priori the covalent angle, so it means that we have also the distance between I minus 3 and I minus 1. And it's missing just the distance between I minus 3 and I. But we are interested in to determine protein structure using data from the NMR, nuclear magnetic resonance data. And this machine, these experiments, can detect distance between closer atoms. And in general, the pair of atoms related to I minus 3 and I can be detected by these experiments. So our hypothesis is realistic. And using geometry, we can also, if we fix the first 3 vertices, the other 2 can be obtained by intersecting 3 spheres. So first, let's partition the set of edges, and we call ED the set of vertices necessary to discretize the search space. These are related to our first hypothesis. And the other set of edges is related to the instance of the problem. For example, we can suppose that the edge in the set EP is provided by the NMR. So the first set can discretize the search space, and so we can associate a tree to the search space, and we can define a branch and prune algorithm in order to find solutions to the DMDGP. So let's call X to the set of solutions, and we are interested in to count the number of solutions of the DMDGP problem. So why is important to determine the cardinality of the set of solutions? So first, because suppose we have an instance associated to some protein, we can, if we can calculate the number of solutions, we can suppose we are talking to a chemistry interested in some protein, and we can calculate the number. If the number of solutions is very high, it can be strange, because depending many of other physical chemistry is not true. Or if the number of solution is just 1 or 2 or 4, it can say that there are some errors in the distances. So it's not a mathematical